Okay, so while playing around with the case statement, I actually realized that we might need the dispatch table because, yeah, like in all examples that I did, we didn't really do any polymorphism or anything like that. We just did imperative programming in cool, right? So um, we just statically typed everything. We didn't really, take the dynamic type of an object. So yeah, and while I was doing the case study, I realized that we, I mean, we implemented it, but I'm not really sure how to be able to call the methods. S- I think it's easier to show with an example what I'm trying to say. And yeah, let's go into the test, right, and create a new test for OP, for example. So when you have a base class, right, and it's like, say it's a print, should return IO or object. I mean, let's keep it simple. Let's do object to not, and it should do something like new IO out string base class, and let's put a new line. Okay, and now let's have a derived class, right? So guess close enough. Now let's have main, right? And main should be maybe something like x is gonna be base class, and let's assign to it new derived class, right? So the static type is base class, but the dynamic type, which is actually inside of the object, is derived class, right? So when we do something like x.print, right, we would expect to see derived class as the result. But since we statically typed everything, we get the response for base class. So yeah, if we take a look at this, oh, it's should be 15 minus OP. Okay, oh, it's inherits. So see, we get base class, but that's not really true. We should get derived class as the result, and that's mainly because in the source code, if we take a look at what main does, is that it calls to base class.print. It doesn't take into account what the x variable is. I mean, we just put it uh, as self, right? But we don't really dispatch to its print method. So here we should do something like load the dispatch table, which we deleted, yikes. Then we need to somehow define the order of the methods in like a nice order, to always have the same order. And yeah, I mean, it shouldn't be much different. We might have to change just the dispatch method, like the where we generate the function calls. And I think that should be everything. But I mean, obviously, it's gonna take a while because it's gonna be a bit annoying to do, right? So another thing, right, is having the methods in order, right? So that's another thing that I'm worried about a bit. So if we look at base class, the methods inside of base class, we can see that it has these methods, the ones from the object and the print. And derived class is, I guess, is the same. See, it has all the functions in order, and here is derived dot print. But if we go back here and add another function, let's say other function, and we don't add it into here. Now if we take a look at the implementation mapping, here we see, okay, it's abort equals print other, but in this one is other is first, right? So I think it should be in the order of the methods. So print should come first, but yeah, like we should say that it's actually on this type. Or I mean, this is just annotation to see which class we are on. But yeah, print should come before other, so we can have the same order of the methods. So when we call the method in assembly, we can use a number as the index. So we no longer use the name. And yeah, I mean, I think all in all, it was a pretty cool find to like try to use first just try to use call on the method name, and now we just hit a roadblock. It's impossible to have OOP with that. You need some kind of dynamically chosen methods so you can have OOP polymorphism. So yeah, that's what we need to do. I think we have to change the when we build this thing. I think it's gonna be easier, so might do that. And then as I said, I just have to add the dispatch table back on all of the objects. That's I mean, that would require us to change the constants. So here in the constants we show the size, right? So we show the size, and then we show all the attributes. So the object is pretty simple. It's gonna have the tag, and the tag is basically the name of the class. Then it's gonna have the dispatch table here, hard coded, and then we just need to not forget to increase the size by 1, because it's gonna be +1 because of the dispatch table, like +1 more keyword basically. And yeah, I guess yeah, because it has the length, yeah, that would be everything here. We just need to add it because I already had the dispatch table, so just copy pasted it back in the code. Wasn't really complicated. The only thing, yeah, it's just to have the methods in order. So if we now take a look at this and look at the dispatch table for our classes, I just have to find it. Should be before init, I guess. Okay, it's here. So we have the dispatch table for the base class, and as we saw earlier, it's print and then other, but for derived class it's the other way around. So we just have to make sure that in here they are in the same order so we can index them. And yeah, I mean, let's go ahead and try to implement that actually. So let's go to the implementations mapping, and here how I did the implementation mapping was, we first take the current class, we get the name of it, we take the context, and the context contains, I guess, let's see, the class context is the list of methods. So that is pretty useful when building the implementation mapping. And then we iterate through the inheritance chain. We go to the parent, we go to the next parent, and so on. And we go through all the methods of those parents. And one trick to have the methods kind of in order was to iterate in reverse. And at the end, where was it? I'm pretty sure I used like reverse on it, or maybe I did not, I don't know. Yeah, to be honest, I don't remember exactly. I was living under the... Anyway, so yeah, we kind of did it in reverse here, but that's not really enough because we take the methods from the current class, then from the parent, and add them. So it's not really gonna keep the order. I'm thinking maybe we want to iterate from the parent class, right? From the parent, and actually add the methods as they are. And if we encounter a redefinition of a method, instead of adding it, we just modify, let's say, I guess the class, I guess the parent name, we should modify it because this is the second type. So this is the class name, like which class has this method, and this guy here is the type on which we make the dispatch. So this should be the latest implementation of the method. So yeah, that's what I'm thinking. We should start from the parent. The only issue with that is I think we have to do it recursively though, because yeah, although I don't like the idea of doing it recursively, but like implementing this that stack kind of data structure. I mean, not really this because we have a stack, but I mean, I guess it would be a good problem to convert, like to learn coding, to convert the code from recursive to a while loop. That would be a fun challenge, and not really because it's hard, but because it's tedious, to be honest. And yeah, I mean, you'd see someone suffer, so that's always fun. So yeah, here we take the class name. So let's try to make this a bit more nice. So let's do another function, static void implementation mapping class, for a single class I meant. So let's pass in all the arguments, right? So this guy is gonna take in an unsigned int class index, because I mean, why not just move all of this code, all of this, into a separate function. So let's take it, move it here. Alright, and here we need to call to it. So please do the work instead of me ChatGPT, and okay, so instead of I, it's gonna be class index, right? So let's reformat the stuff. Okay, here we can actually just return. We don't care about cell type. It's not really a type. It's in here just for the memes, as we all are. Just so we don't find it undefined, basically. But it's not really a class. It's more like a meta class meta thing. I don't know how to call it. Okay, so yeah, here we go from the current context. Yeah. So if we start from the parent, we would keep the right order. So that's the most important thing, to start from the parent node. So then why don't we I mean, I guess one thing we can do just to make it funny is let's make a while. Let's make it. Let's implement the recursion in a while loop, right? Like it's gonna be pretty fun to attempt that. So we need a current class, right? So how would we do it recursively? Is, let's say we have a function static void. It's gonna take a class context, right? Let's say like this, right? And here we have the condition, the base condition, right? If the this thing is equal to null, then we should probably do something. So let's say class context, and otherwise we call it like this, right? So this is the base class. I think it should just stop, probably, not really sure though. And then after the recursive call, here we do the stuff. Basically here we do the stuff, and the stuff is actually the contents from inside of the while loop, right? So that would be done there. Of course we would need to pass in the pointers for all of the other arguments, and at the end of the call we get it in reverse, basically, because it was called recursively, and not really because it was called recursively, but because we first went recursively into the inheritance chain and then we did the stuff. Because if we do it like this, I think it is the same thing as doing a while loop, because we do the stuff, then we go recursively, then we do the stuff again. So yeah, and basically doing it like this is like having a stack. So let's say stack where we have a like something like this. The current class, it's on the stack, then we push on the stack the parent, the parent2, and so on. And now when we reach the end, so we do the return and reach this other side, we basically pop from the stack. So we pop parent2, we pop parent, and then parent. So that's the idea. So let's try to do that, but in here. So we are gonna need to go in ds.c, and let's define DSLL. We are gonna need the linked list, basically. DSLL linked list. Let's call it class stack equals to null. DS linked list init. So we are gonna have pointers to this guy. Yeah, I don't know why I did it. Okay, and now let's do a while loop exactly like this one. Current context is equal to parent, and here we need to, I think, linked list push let's do push front. And this guy can also fail, but we don't really care. So it gives a linked list and a pointer, a void pointer. So I just have to remember we mem copy it. Okay, so interesting. So let's keep pointers inside, right? Like this. And now let's visualize first this thing. Alright, so let's do a while loop. So I guess now we should get while pointer to class stack. I think I have this function linked list empty. Uh, okay, I mean I just wanted to check. Okay, no documentation obviously. So it returns 1 if the list is empty and 0 if the list is not empty. So we should do while is equal to 0. Okay, we have this thing, right? And let's say that here we have class context, we have the current context. Let's ds linked list pop front. We pop into it. We can take the parent name like here, or I guess let's say class. I mean we already have class name, so yeah, it's more parent name. It's more. So now if we take a look at this, oh that's interesting. God damn it! I have some bugs in this trash library. So let me see. Okay, yeah. So I fixed that. I'll just put here. Let's put like this. So if it fails, it fails. You know. Okay. So yeah. Now we get parent name. In the first one, I guess maybe another thing we can do is do another percentage s, and here let's do class name. So this will show us, let's say, the current context. So for object, the first parent, or the most, like the oldest parent, I don't know, is object. Then IO is like this, string. And we are interested actually in base class. So for base class, the oldest one, again, object. Then we have base class. Then here we have object, then base class, and then derives class. Right, so we get them in order, and that's really good. So now in this linked list, we actually get the parents in order. So we can continue. So let's have this array of methods here, and now we are gonna have to replace this loop with this guy. So this is actually how you do the recursive call, how I showed you. So first you create a stack and you push on the stack until you reach the base condition, and then you have a second while loop where you pop from the stack while it's empty, until it's empty, I guess. And you are gonna get Yeah, I mean, it's gonna be a bit complex to build, I guess, the stack context or something, but you know, you can figure it out. So let's go through the methods of the current class, right? So we take the first method and let's see. So I didn't do any, actually I did reverse. See, I actually do reverse, but I don't think we are gonna need the reverse anymore. I mean, it's for attributes. So yeah, I don't think we are gonna need the reverse in our case. So let's go to the implementations mapping and let's go back. So we were here, right? We go through all the methods. And as I said, I think we need to take them in order. I don't think there's any point in going reverse. So yeah, take the current method, we build this thing, right? We build this thing. Now we should check if we find it. Right? We search and we look for the item. It is the iterator. So we look for another method in our implementation mapping that I mean, implementation mapping is this guy. I guess this guy. Methods, implementation mapping item. Yeah. Anyway. So we basically look for another item that is made for this class that we are currently on. So that would be like for the current class context, like base class here or derived class here. Then we need to look at the method name. We check if the method like pair. I guess I didn't show the method name there, but anyway, you know, like the method itself. And if we find it, then I just said break, right? But I think we actually need the index. So I think because here we need to do replace the method basically, and then continue. So let's see how we can do that. I think the easiest way to do it is to have found and an unsigned int for the index. Unsigned int l. Right, so we do like this. So when we break, l is gonna keep its value. So that's the easiest way I can think of. So if so here we said if found we continue, but it should be, let's say if not found we do something, and else we do something else. Right, so if we don't find the method, then it's the same thing as before. So we just copy paste this thing. So if it's not found, we just find the class node for some reason. Wait, let me just check. So here we find the class node, then we find the method. Oh, because we need some extra annotation. Yeah, sure, why not? Okay, let me see. So I guess what the implementation mapping also has the method on it. That's interesting. So shouldn't we do this for every case though? Why do it just there? I think we should do it every time. Why not? Like it's not really that oh, it's inefficient. I mean, the entire compiler is inefficient and it's still pretty fast. So here, let's say method. So we initialize the item like this. I mean, sure, we can do this entire part. We can do it in here, right? So we can do it like this. And here we just need to say class name and method name because they are variables and it will still work. And now it's a bit more efficient, right? If you really wanted it. So on the else case, as I said, we need to replace some stuff. So we need to replace the parent name and I think also the method. But yeah, I mean, it's pretty interesting that this guy should be done outside, I think, because it's gonna be calculated also on the if case and also on the else case. I can see that. I guess also the method. Wow, interesting. Interestingly enough, also the method is gonna be done like that. But on this case, we're gonna have a reference to an item, which is gonna be equal to null, and then we need to do dynamic array get into the methods array index L. Man, it's so ugly to have index L because it's oh, we can use I for this guy, right? Because we don't have any I's. That would be bad though. And here we can use J. So I is the what? The method, and J is the okay. So let's see again. So we go through all the methods. We take the method context. We take the method name. Then we go through the implementation mapping methods of this class. Okay. And if we find an already existing method there, we have to do something here. So if we didn't find it, we just add it. And this will be basically added in order, I think. Hopefully. We'll see. And if we found a redefinition, basically, so if we look at OP, the first time we'll go into base class, right? So we are gonna find print, which is totally new, so we add it. Then we are gonna find other, so we also add it. And then we are gonna go into derived class. And we are gonna find print, which is no longer new. So we have to actually just replace this guy with this thing, right? So we have to overwrite it pretty much. So pretty easy. And here we just need to set the method. So that's the contents, right? And the other thing we need to set is the parent name, which by parent name we mean this name. It's a bit weird, but the parent name is like the name of the iterator. I don't know how to call it. and I just chose parent. I mean, it is parent though, if you think about it, because it comes from the ancestor, and it just happens that the current class is the last one in the stack, so it's also called parent. So yeah, whatever, it is what it is. We just have to deal with that. So now let's see what happens if we rerun this thing. So if we take a look at this, they're in reverse. That's really strange. Why are they in the reverse order? Although see, here it kept the order, so it kept other in the same spot, and here for print it just changed the parent name, right? And probably also it changed the implementation. So I think this is really nice. Oh, I know why. It's because we didn't delete this while loop. So yeah, basically we just rewrote this entire while loop, right? So what we have to do is delete it. And here we just need to go okay. And I guess since this thing is the same as this thing, I mean it's pretty much the same thing. Let's rename this to J. So we go through our methods, we take it and we add it to the implementations item. Here I can use, have another cool function, append many, but and I should make a version where you can merge two arrays, because here we just extend our bigger implementation mapping with our current methods. So we just save the state. It's nothing special. Okay, so let's see again. Okay, now they are in the right order. Just forgot to remove that. I mean, the while loop was fine because it wasn't running, but here I was doing the reverse. Yeah. But now we actually get the the classes to keep the order of these guys. So let's take a look at the assembly. Let's see if the dispatch table looks the same. I mean, it should, right? So we have the base class, abort, type name, copy equals print other, and yeah, that's really nice to see. The print and the other are in the same order as the parent. And yeah, that's important because we are gonna have a base class, and if the inner thing is the right class, then it can call any method from the base class, because that's how objects work. Like if you have an interface, then you can call methods from that interface from the child class. And yeah, like the other methods that come below this other are not important for this relation between derived and base. Like you won't be able to call those functions basically. So if we, for example, go into OOP and we define here, let's say custom or something, I don't know, you won't be able to say here custom. It should give us an error. Yeah, undefined method custom. So because custom is not on base class, and even though it's in derived class, the static type checking is done statically, and that was the problem because we also compiled statically. But now if we just print call to print, this should be fine. And if we check the dispatch tables, let's see the dispatch table, we should see that custom is added at the bottom, but in fact it's not really important on the order because you can only call these functions, these methods. So yeah, I think everything is good now. So let's go into go. So we have, I guess I fixed the das.h compilation error. Anyway, added this test case, but it's not ready yet. I guess we can have something like yeah, and something else that's gonna be interesting is okay. So let's have a more complicated test case here. So here we do xprint, right? We do xprint. What if we do x at base class dot print? This guy should actually show this thing. Then let's say we have another object. Let's call it y. Let's create a derived class. Here we can actually call to custom, but we can also call to base class dot print. We can, I think we can cast it. Let's see what happens if we, yeah, it actually works. Okay, I just wanted to go in the like history. Probably, yeah. Okay, let's save it like this. So it first shows base class, which is not correct yet. We have to use the dispatch table. Here it shows base class, which would be fine, obviously. And here it also shows base class just because it happens. Well, I guess these are static dispatches, so it's fine to use, yeah, whatever. We will have to see. But yeah, let's just create 15 ref.15 op.ref. So I said we expect to see derived class, base class, custom, base class. Okay. So now we can actually just add these tests. And here we did implementation mapping. I don't know what I did in the assembler. Probably just some to-dos. And I put back the dispatch table. So I don't know. Let's just say some comment. So as I said in the object prototypes, we have to add back the dispatch table. I mean, I guess I already opened like the commit where I last had it. So let's go ahead with object prototype. We'll just copy space from here. So what we had here was adding this tab, and obviously we need to increase the size by 1. I think that was all like in the definition. Right, that was the only thing. And then for the constants, I think that's the only thing here. So emit const. Let's see, emit consts. And it's this one. So for this one, like we would have to add that, like let's say we have the size and we have to add it like this, but we need to also increase the size by 1. We added a new word in our thing. Then for the int constant we need to do the same thing, but for int, and boolean is I guess the same. So this should add back these things, although now probably something changed and I'm not really sure what. Like we increased the offset to our attributes, so we have to make sure that we check that. So I guess here we don't do anything on the attributes. Initialize attribute. Okay. So we do something on expression and then we emit store variable. So let's see what happens. So this is not important. Method is just for arguments. Class is what's interesting. And here, as I said, we increased by a keyword, so we have to add 24. Right, we have to add 24 there because this is the index to the first attribute. Index to the first attribute. And another place where we might have to change that is it's interesting. RAX ident. So here we need to do 24 also. No, this is the yeah, that's fine. That's the function argument. So I meant here we need to do 24. I mean, it's gonna be easy to check because we have the test cases, so we can see if they still pass because we didn't really change that much. And here we have the identifier attribute. So the attribute slot is also going to be 24 plus 8. Well, unreachable. Hopefully it is unreachable. This guy should also be 24. So let's run the checker. I think that should be all. Okay, and obviously that wasn't it. hello world. It is almost right, but not quite. So let's go into the assembly, and I think here we need to change these guys. So this should be 24, 24, 24, because it shows us like an extra keyword of the like two, I don't know, the extra 2 bytes for some reason. It should be 32, and this page table should be at 16. Bruh. Okay. I think we don't have to change anything here. Like copy doesn't call to any function, so it's fine. Abort. I mean, even though it calls to IO string, it's like these are static. Like it works to have it static. Like that. Here, object copy again. It's static. All of these should be static. Okay, perfect. So, and here again, it can be static, so it's fine. Now let's see. We get a hello world and checker as, and just to have it faster. Okay, so equals is not implemented as well, but we'll do that after we fix the problem with OP. So we actually feature add back this table. Yeah, it's a bit ugly that I used numbers like this, but um, I mean I can do a define uh, or like attributes offset is 24, and then let's search for so this should be attribute offset. Interesting. This is also attribute offset, right? Like this makes it a bit more it's attribute offset, yeah, and we can change it however we want, so we change it in only one place. Anyway, we should probably do the same for this thing, although probably, I mean, there are only two. Okay, let's do that. So we have define, let's say, arguments offset is gonna be 16. Okay, do we have anything else a bit stupid like this? I guess this guy, this should be locals offset. Define locals offset. The problem with this thing is that we have a lot of them. Right, and let's say define word size is gonna be 8, just to also word size. Like this is how whoa. Yeah, really interesting how I mistyped twice. Anyway, again, this is like word size times whatever. Now, I don't even know what this thing does. Oh, it's yeah, freeing the stuff. Okay, next. Okay, now we use word size. Mhm. I mean, say define ident size. Let's be. It's like indent. Oh, we already have indent size. That's bad. Probably we should, append some name to it. So let's see. These should also be maybe computed somehow. Yeah, just, I mean, there are too many. Let me do a macro. I mean, we'll know if, no, we broke something because it's gonna be like, oh, we can undo it like this. I think I missed one, but we will come back for him. I guess you can also do like query replace. And yeah, search for like context and for and replace. Man, how many? Okay, perfect. So we still had that one here. So if I do, okay, let's just make sure that we didn't break anything. Okay, perfect. Just to have less, magic numbers. But yeah, we still have this magic number. So anyway, let's just format and say that here we just wasted some time. Factor refactoring. Fancy way of saying that we wasted time. Okay, that I mean just a joke. It's good to refactor the code. I mean, literally, it's good because now we have this attribute offset, and it's more readable what happens here. Before we had 24 plus 8 times offset, like that was stupid. But now we see, okay, it's the attribute offset plus the size in bytes or whatever. Yeah. Um. So I guess the dispatch call should be next. We should tackle the dispatch call. So Yeah, here I can see that we load self into rocks, into the A register. Here we push all the arguments on the stack. So they're on the stack, the arguments are on the stack. We have self in the A register. Here we do some useless stuff. Okay, so here instead of doing call, we should do probably something else. So we might have to take the A register, which contains the expression on which we call the function, the method, and we need to go to the dispatch table of it. So let's have define dispatch table or disp tab. This table offset is going to be 16, right? So we need to go to that offset in our object, right? Load the value from there, so that's going to be like a pointer to something. I guess we can look at an example just to see the dispatch table. So we're gonna have a prototype object, right? So we're gonna have something like maybe a string, for example. So we need to offset it by 16. Go to this guy, take the value, and this is a pointer to a disp table. So let's see where that guy lives. Okay, so it's here. So it would bring us here. Then we need to go through all the methods, like the method context that we have, check for the name, and if the name is equal to any of these, return the index and just call that address. So yeah, we have to call that address. Okay, perfect. So we have the plan. The only extra thing is we are gonna have this instruction type. And I always set it, so I should make it null whenever it's not a static dispatch. That's something we have to do inside of CodeGen. So when we implement our tree address code, right, we have a dispatch full and a simple dispatch. So simple dispatch is just method calls that will have to go through the dispatch table, and full dispatch is the static one. I have no idea why I called it. I mean, it's whatever. So static dispatch has to set the type like this. Bam. Set the type. And then calls to... Wait, where was it? Okay, I mean, it does it like this. Doesn't matter. Right, it sets the type. And for this one, I set it to self type. Wait, what? Oh, so here we said if it's null, then we... Ew. Ew. Can you let me remember if you can illegal. I was losing my mind. Okay, semantic.c. Let's check for illegal. Is class name. Okay, I want to see something for dispatch. Like, can you? I think I remember precisely that I searched for this thing once before. I'm pretty sure. Semantic check dispatch expression. Can you have static type? It can be self. Okay, but if it is self type, then I wait. What? But why do I? Here I said if it's illegal. But why do I check this? Because it's. Wait, am I crazy? Here I check if static type is null. Oh, static type is expression type, and if the expression type is self type for whatever reason, what? Hopefully this is fine. Wow. Hopefully, yeah, hopefully the self type won't come to bite us in the ass later. So yeah, static type is like the type of the expression, and like what it can be, maybe self dot. Who knows? Let's go back to our thing here. So here, let's say, well, if it's null, then it's null, right? Like it is what it is. I mean, the dispatch full is more like calling the method on an expression, and here we check if we have or do not have a static check. So if we put null, I guess we should just do this instead. So this can make it null though, right? This is a const, and this is not a okay, but this can make it null. It's nullable for this one, and for the simple one, here I said it's always gonna be self type, whatever that meant for me. Um, I think we can keep it null, but the expression should be self. Or I mean, expression could also be null, and here we check if the instruction is null. So it might be easier. Okay. So here we need to check if expression is equal to null actually. Then we load self. itself. I mean, it's pretty obvious that it's gonna be loading self. Okay, and here we're gonna have instruction type. So if instruction type is null, we have to do some stuff. So let's see. If this guy is null, we are gonna need some to do. On the else case, if it's not null, it's not gonna be self type, obviously. We're gonna need to take the class name. It's gonna be instruction type. We have to compare. Okay, so here we go through all the methods. So then that means that probably the if else should be outside, should be here. So we check the instruction expression on which we call the method. If it's not existent, then it's on self. Then we check the instruction type, like the dispatch type. If it's null, then again doesn't exist. So we have to use the dispatch table. But if the instruction type exists, then we have to do this for loop, I think. And we can use call as before. So we have to do it like this. So if we have the dispatch type, we just go through the implementation mapping and find the method that works. Okay, let's do a DS panic. And let's see. I was hoping it's gonna, well, I guess, okay, it failed. Perfect. So dispatch call without a type. So yeah, this should be interesting to do. Let's see what changes we made, just to keep it in mind. So the dispatch, this table offset, we did changes only in here, that's good. Let's update the codegen printing, because if we are gonna run the checker on 3 address code, it's not gonna work. So let's go into, which test is it? Or I guess, yeah, 12 duck dispatch. So we have, oh my god, it's I mean, it's quite a lot, but so I guess I can do something like that. It's easier. It's 12. Okay. Enable syntax, and we have something like this. So this is b.f. So it shouldn't have this. It should be just like that. This one's fine. And I think this one should be like this. I think this looks good. So now let's go into print tag, because probably it's gonna dispatch call. Yeah, probably it's gonna die. So let's do step by step. So we printf this part. then if dispatch call expression is not equal to null, we have to print it. Something like this. Obviously we can only have the type if we have the expression, but yeah, whatever. Like this can go inside of this if, like it can only be there, I guess. Right. And also we also need to always print, yes, print a dot here. After the expression we always have a dot. And at the end we are gonna need this part. Right. Something like this. Let's see if 12, the 12th test passes. Doesn't pass. Interesting. What? T0, T0? Are you... Why are you annoying? So, well, B. Okay, so we made a mistake in codegen.c. So as I said, if it's a dispatch, yeah, here I made a mistake. It should be dispatch full. It's like type. We need type. Why is it complaining? Because it needs a dot value. Yeah. Okay. Now it looks good. So let's see, the checker passes and the 15th test now. 15 dot case, or what's the matter? So here is abort. I mean, I don't see why it wouldn't work. It should call to abort like that. I forgot to update the... Yeah, I forgot to update the test. Okay, so now we should be fine. So let's first of all do not include this file first. So this is feature update fields of this call in duck in 3 others code. And yeah, now we can actually do the thing. So first, like step 1 is to get a dispatch table. Step 2 is to get a method address. Step 3, call method. It's pretty simple. So to get the dispatch table, which yeah, we just need to look at the load variable. It should be similar to loading a variable. To do something like this, the comment will be null, and we have to move into RAX, let's say rex plus this table offset. I think this should do it, right? We move into the A register, A plus offset. So that should take the dispatch table. Now getting the method address is a bit more interesting. I think we still need the for loop of some kind. So let's take the for loop. We put it here, right? We need this, right, to continue. So if is it right now? I think it is. Oh no, because we don't have instruction type. But yeah, then how do we get the method address? I guess the method address is just the first time we encounter the method name in any class. So that's one way to do it. So we have this call, right? We don't have expression or type, we just have the method. So that's what I'm thinking. So it's a bit of a hack, I guess. But let's take a look at the map. I just wanted to view the map. I guess we can view it for anything. So the hack that I have in mind is, let's say we search for this one doesn't have anything interesting. Let's look at OP. Let's say we search for other, right? Let's say that that's the function we search for. So we go through all the classes, we don't find it, and here what we have to do is, okay, we found the name base class, so here we start indexing. It's index 0, index 1, index 2, index 3, index 4. Oh, and we also found other, so it's index 5, and it's index 5 regardless of what other class we have, right? Yeah, because they are in order. Okay, so we can do this thing. Okay, so let's say size t method is not really offset because it's not gonna be in bytes, it's gonna be method index char pointer current class name. Where do I have like class from? I, wait, where is it defined? Context current class. Ah, I mean, we don't even need to do that hack because we have the current class. Wait, but I mean current class. Wait a second, current class is completely useless. Yeah, whatever. So here we take nothing from that. So we do class name and here we need to check if class name is equal to null or the class name is not equal. Then we have to say that class name is equal to that class name. It figured it out, that's cool. Probably also, no, yeah, it's right, not continue. We can make it const. Const char means just that we are not gonna modify the string, not read the pointer. It's like const in JavaScript, if you know what I mean. Okay, so here we found a new class. So we go from the beginning with the index. And now we have to search for the method like this. We compare the method name with the instruction, and I guess if it's equal, so if find replace equal, I guess in this case we can break, sure, and we have the method index, and yeah, that's everything. So size the method offset should be this, and now we need to load into RAX. Okay, 1 second though, because here I basically just overwrote RAX, but does it matter? I think so. I think when we do function calls, okay, let's use like, I don't know, like RDI or RSI or something. RDI for the thing. So in RDI now we have the start of the dispatch table. So if we add method offset to it, we should, and also dereference it maybe. I don't know if we should dereference. Yeah, I'm not sure. So when we do it the first time, here we add into, so we have our prototype object, right? We have our prototype object and we add some value like the dispatch table offset, right? So that would give us a pointer to the dispatch table. So if we dereference it, we actually go to the dispatch table. So we get the value where it's in memory. So like the first, let's say the first value in the dispatch table, which is, I mean, a pointer to a function. But and then here, if we add the method offset to the dispatch table, we get another address. So we should probably just load address, and that doesn't look okay. Let's man, if it's not possible, we are cooked. Assembly call call method at address of register. mean, you know what? Let's just do it, see if it works. And it is what if it doesn't work, then we are cooked. Then we are cooked. I mean, we should, you know, jump to that address. We can probably simulate calling by doing, you know, push the return address, which is the next instruction. So we just push on the stack RSP plus 8 or something. And yeah, probably. Let's see. Again, I used A. Okay, let's it's 6 segmentation sorted. Okay, so probably like surely there's a problem with that. So let's just go ahead to a bit of manual labor in GDB. So let's see. Okay, so straight up we have a function call. That's perfect. So in RDI we have okay. That's to be honest, I have no idea what happened. So let's go ahead one more time. So we push RBX. That. So we move. Okay, what we do in OP that it's so fast with a function call? Is it x.print? I think so. So we load the first variable, which is a 6. I guess it's a like should probably be a 6. It's a base class. So we have something like this. Object is 0. Hmm. Let's see what you know this tells us. So probably it's like 0, 1, 2, 3, 4, 5, 6. So at least we get the right class right in the object. I mean, we got it before, but no. So here I said that we load in RDI the dispatch table. So I would expect that if we take a peek at what's inside of this guy, I still don't know how to do nice prints. So we have 06, then I think we have the address. Let me just check the prototype objects because I think it doesn't look good. So, oh, because I'm using hex and it's like this is the first, this is the second, this is the third thing. So we have, yeah, it actually looks good. So we have some address there, 4160 dB. Let's see. Oh, okay, so maybe we should do load address for both of them. What? I mean, that's a bit strange. Because I don't know how to make it actually go there. So let's see. So here we, as before, we moved this guy, right? So if we examine again 24 hex from this address, then I have to learn again how to use this really shitty command. So let's take a look at what we have at this address. So it's, I think it's like this. So we have random stuff, right? My hope is that we are gonna have in RDI this thing after this step. Okay, I mean it's funny, it's called dead 9. Um, but wait, is it? It's not. Oh, it's, see, we loaded the like this thing plus 10 plus 16. So probably we should dereference it once. Maybe that was fine. And here I didn't add any. Okay, I think I know where I made a mistake. So this move was fine. But I see that method offset is 0. What? How is that even? Oh my god, I forgot to increment it. But it still didn't work, so I mean it's fine, it's fine. Let's see. So here we load that thing that I said. Like I don't remember the address now, but I guess you do. So in RAX we put self, which is 06, basically like a 6 type. Now we load from 38. So we load. I mean, it looks familiar. Probably that was the thing. And now in RDI we should put. I don't even know what exactly. So from plus 32. So it's like the fourth method. It's like the fourth one. The fourth method. Let's see. So regardless of base class, this is at 0, at 8, 16, 24, 32. So it found the right offset. That's at least that's good. It means that our algorithm works. So we load. I don't know what we should load there though. So I mean we see the push RBP. And here we try to call it. So here we try to just, call this address. Can't we just call an address like that? Or should it be this one with C2 step instruction? I mean, let's just try to use move. It works. And that just worked. Holy shit. Okay, let's run the checker. And now we have it. Now we have the real way of doing it. I guess that's pretty nice. I mean, it wasn't more difficult to do it than when we had just the static dispatch. It was a bit annoying to get everything set up because we had to backtrack and change some stuff, but no, it's pretty nice. hmm But now we have a problem with equals. I mean, we don't have equals, obviously, we have a problem with it. But first, let me just feature actually calling methods. That's nice. Let's just delete some of this garbage. And let's see. I mean, here we also have some. I just wanted to see what's our status on the main.cl file. Like, if we manage to compile this file, it means that it's complete. Well, obviously, we are going to implement at least rule 110 in this language. Maybe game of life, but it's a bit hard because we don't have lists. So yeah, let's take a look at our prelude. So yeah, if you don't remember, we also added this extern keyword to make our lives like, maybe in the future we'll be able to have like an LSP, and we might need references to tokens themselves or something. Don't know how LSPs works, but just a guess. And I also have this idea of maybe adding more functions. So for example, this AND function. It's pretty interesting. It's just we cannot really use external attributes, so I just made like a hack, right? And I think that the AND function is pretty funny though. So you can have, like, we don't have AND like this in cool, so you would have to put a lot of ifs, and I thought, why not just make this kind of method. And yeah, it looks like it actually works. But we still have some to-dos here, so we need to implement the equals here for reading a string. I'm not really sure if we handle end of file correctly. Like, I'm not sure what would happen if you pass end of file into this. Like, I remember that the read line from C actually stops if you give it an end of file, so I'm not sure how to handle that, because here we check we check if we read a new line, and if we read a new line we stop. But I don't know how to check if we read an end of file. We'll have to see. So what would be some other stuff? I guess in the assembly we have to implement equals, and I just made it as a function, so we can actually overwrite it in other methods and implement custom equals. That would be cool. But yeah, just for equal it will work. Anyway, probably, yeah, since you cannot really inherit from int, it doesn't make sense to have custom plus, but that would have been fun to have. So the other stuff that we need is probably to implement concat, like string concat and string substring, and obviously the equals. For integers it's gonna be easy. For strings, I mean, I don't know. And then for object, wait, let's look. And then for object, I mean for boolean is also easy. But for object it's just gonna be checking if the references are the same. So yeah, it's like the default. I mean, I even think that we don't even need to implement it in assembly. We might be able to. No, we cannot. Mm. It would it would just be recursive calling. Yeah. I mean, yeah, no. It's not a good idea. It's just because, for example, for strings we have to do mem compare. We have to compare the memory itself. For objects, it's gonna be like the default implementation is gonna be checking if the addresses are the same. And yeah, but it shouldn't be really difficult. It should be easy-ish to implement. But yeah, I'll try to do it like next time. Probably we'll do equals, right? And I still have to make. Yeah, let's finish the assembly, like all the functions, also substring and concat. And one more thing, I guess in the assembler, do I have like a to do? Yeah, so um, now we have the dispatch table, but the case doesn't really feel right. So let's because I was playing around with it, let me show you my idea. So the idea is pretty stupid, to be honest. We have the type, and we build or at least we find a constant with the type, right? We have to check if an expression is instance of some type. So we search for that type, right, in our constants. Then we make a function call to type name. But as we saw, this should be maybe, yeah, I don't know. I mean, it's fine to be a static dispatch because type name works by tag. So we have type name, and this guy returns us the string, which is the same constant. So it would be the same constant as this one if they are equal. So then that's what we do here. We check if those two constants are equal. Basically that's the idea for isInstance. However, this doesn't really work. So let's say we have a test case. Let's make a test case that won't work. So case more, I don't know. So let's take case and let's say we pass in an IO. So out int the method and we pass in new IO. So new IO doesn't match with anything here, but it should match with object because object is parent of IO. So yeah, that's what I have no idea how we are gonna implement that. Well, it didn't work because I forgot. Yeah, see, it doesn't like that. Calm down. So it's gonna say for what? Randomly printing stuff. I mean, because we don't. Yeah, so we check for equality between the names. And that doesn't work. So, to be honest, I have no idea how the case should be implemented. I mean, isInstance made sense? Still makes somehow. But yeah, like because the type is gonna be dynamic for this object, so it should match with the object. It's a subclass of object. Like even if we had, let's say, let's make another another test. Class A doesn't have anything. Class B inherits A, and here we say something like if it's A, we do 3. If X is B, we do 3 and 2. So here if we say new A, it should probably print A, but if we remove, no, I meant B. If we do B, B inherits from A, so this match should be taken. But yeah, it doesn't work, right? So how are we gonna check inheritance in assembly? That's gonna be an interesting thing to figure out, I guess. So that's probably the last thing, one of the last things that we have to do in the assembler. So this function, which doesn't feel right, whatever. And the other one is casting an object to another object. So my idea is to just change the tag, and I think that should do it if we change the tag of the object, because we just cast it like for example how prototypes objects are, or I guess constants. They have the tag, this is an int, and let's say we can cast it to something else. We just change the tag, and that's it. Like if we cast it to an object, we just change the tag to object. We might also have to change the size. But I don't know. Like if we change the tag, type name is gonna print something else. Methods, if you call methods on it, something else happens. Mm. To be honest, I don't know if we need to change the tag. Like here, for example, for this one. Okay, X is of type A. That's true. But X is still a B, though, in its true form, in its heart. Sure, yeah. I mean, let's check. I mean, we can check with the manual. Let's take a look at case and maybe also at operational semantics or something. Let's go down. Probably this is for the case. Man, that sucks. So, case. Okay, so C is more than equal. What the fuck? First expression 0 is evaluated, so we evaluate this one. I mean, we do that. We do basically all of this thing. The return type, we know it. No branch. So yeah, I mean, we do this thing, right? So this is done. I'm curious to see this part, or how it works. I guess, yeah, like up until this point we managed to have just print a hello world, have math operations, all kind of math operations, have if statements, while loops, also works with let statements, and calling methods, both like doing static dispatch and normal function calls. The case statements is still a bit in a gray zone. I don't know. It's not fully ready yet. But I mean, it's usable. Like we have a test case that works, one that doesn't. Sometimes if you, like, have it really simple, it might work, but it's not fully done yet. Yeah, obviously you can create classes and stuff, and also have to implement equals, like checking if two objects are equal, and being able to redefine that function and have custom equals. That's the first step into having custom operators. And yeah, like the OOP features work. We just have to implement case to be able to use casting, because we don't have casting, but we have polymorphism, so one step towards OOP. So yeah, I guess next time we have to finish the full assembly. That's like comparing between doing the assembly and the case statement. Doing the assembly is easier. We just have to implement substring, concat, and equals. And for the case statement, I have no real idea of how to do it. So obviously it's easier to go with what you think you know. So I guess that's what we are gonna do next time. So yeah, uh, okay. Let's take one more look at our outputs. I mean, still let's take a look at the main. So this is the example main.cl. Okay, it works. Like it works to generate the assembly, but it's not gonna work to actually run it. So yeah, main.cl. So this is gonna be our let's say hardest test to be able to get this thing going. And yeah, then probably we are gonna add a list to our prelude, maybe a matrix, I don't know, whatever. It's gonna be a list is gonna be for sure there. And yeah, we actually are almost there. Just a bit more assembly and fixing the case statement. So I'll see you in the next one.